Hello everyone, I'm Siheng from University of Chinese Academy of Sciences. Today I'm going to talk about our recent work, fine-grained respiration monitoring during overnight sleep using IR-UWB radar. This is the overview of this talk. It consists of 4 parts. Let's begin with background and motivation. Respiration during sleep is an important indicator of human health, which can reflect the progression of some diseases and decline in health. Respiration disorders during sleep affect the quality of sleep and cause fatigue during the day. What's worse, severe sleep disorders such as SAS can increase the risk of sudden death in adults. Therefore, it's important to monitor human respiration throughout the night. Traditional methods for continuous respiration monitoring are intrusive and require the subject to stay in hospital or sleep lab for a long time, preventing them from wide deployment and in-home use. Recently, wearable devices such as flow chest straps have been developed to detect the respiration state, but they make users feel uncomfortable while wearing them overnight. The alternative solution is the contactless sensing. It's non-intrusive and easy to deploy at home. And among the wireless signals, IR-UWB radio signals are less sensitive to noises and can support high temporal resolution, so it provides a more promising solution for overnight and fine-grained respiration monitoring. However, existing solutions on respiration monitoring mainly focus on normal conditions. For example, subject in a sober state sits in chair or lies in bed, which is not applicable to the overnight sleep scenario. In reality, the subject is unconscious and uncontrollable during sleep. Motions of different body parts will cause changes in distance and orientation between the subject and the device, and work focusing on overnight monitoring is relatively rare. Therefore, overnight respiration monitoring is still a challenge. To better understand the IR-UWB radio signal and use it in overnight monitoring, we collect the signals of an IR-UWB radar in a real sleep scenario, including 3 nights of 3 subjects, and analyze the amplitude and phase waveforms of the signals. And we have 2 primary observations. We observe that the respiration waveforms differ in different locations and orientations between the subject and the radar. 2 examples are shown here. Example 1 is when the subject is lying on the back with his or her sideways chest facing the radar 0.72 meters away. The amplitude waveform is disordered while the phase waveform is regular. An example 2 of different posture and distance is in another situation, that the amplitude waveform is regular while the phase waveform is disordered. It shows that a bad position for amplitude waveform could be a good position for phase waveform, and vice versa. So when amplitude or phase of a received signal is used individually, there are locations where the waveforms are disordered and respiration cannot be detected. We call it the blind spot problem. This observation can be used to improve the detection rate of respiration by combining both the amplitude and phase waveform. We choose the phase waveform when the subject breathes steadily, calculate the phase changes between all neighboring pairs of peak and valley, and then estimate the respiration depth by this formula. We found that the depth is between 0.01 and 0.7 centimeters. However, the depth of 0.01 centimeters is not a valid respiration depth, according to our common sense. The respiration depth we got is distorted. We know that the distortion of the depth is from the distortion of the phase change. That is, the received signals are affected by the multipath phenomenon in the environment. The distance and orientation between a subject and a radar vary during the night. So does his or her sleeping posture. Therefore, the phase we get is in fact one distorted by the superposition of these factors. We should eliminate the effects of these factors to get more realistic respiration depths. So our respiration monitoring prototype, as shown here, consists of 5 modules: signal preprocessing, signal waveform classification, respiration rate measurement, respiration depth estimation, and respiration pattern recognition. We first apply the background subtraction method on each 30-second sliding window to remove the static clutter. We then perform FFT along the slow time dimension to obtain a Doppler map. As we know, the largest amplitude peak among all columns on the Doppler map corresponds to the location of human. Therefore, we take a slice from the 2D original received signal matrix as an estimation of received signal from human body. At last, we employ SG filter to get a denoised target signal waveform. After signal preprocessing, we can get the amplitude and phase waveforms of the reflex signal. Then we divide the signal waveforms into 3 categories: body movement waveforms, respiration detectable waveform, and other waveforms. We identify respiration detectable waveforms by applying autocorrelation on signal waveforms and get the max peak value in the result. If the peak value exceeds a certain threshold and the frequency of the peak is located in the normal respiration rate range, then it's classified as a respiration detectable waveform. Meanwhile, we utilize the complementarity between amplitude and phase to reduce the impact of the blind spot problem observed in a previous study, which is, instead of using amplitude or phase waveform individually, we propose that if one of them meets the requirements above, then the current window will be identified as a respiration detectable waveform, and the one with the higher RAV between amplitude and phase waveform will be used to measure the respiration rate. We show 3 examples of signal waveforms here. The first row is amplitude, and the second is phase. The RAV exceeding threshold is in green, and RAV not is in red. According to the requirements, the first 2 windows are identified as respiration detectable, and the third is respiration undetectable. And to estimate the respiration depth, we have to solve the distortion problem observed in previous study. The respiration depth distortion is actually the phase distortion. We analyze it by projecting the signal onto the complex plane, or we call IQ domain. The decomposition of the signal can be expressed as H equal to Hs plus Hd. H is the superposition of all the path components in the same distance bin as human. The static component Hs consists of reflection paths from different stationary body parts, for example, hand and legs, and static objects in the same distance as human in the environment. while the dynamic component HD is determined by the reflection path from dynamic body part. For example, chest. When the subject breathes, HD rotates along a circular arc, resulting in rotating of edge. Using the phase change theta I during rotating of edge, we can get the respiration depth using this formula. However, theta I is not equal to the real phase change theta C caused by the subject's respiration due to the effect of HS. Therefore, we need to restore the phase change from theta I to theta C to get a real respiration depth. So we fill a circle based on the signal sample in IQ domain. Then HS can be eliminated by translating the circle center to the origin of coordinates. As a result, H equal to HD, theta I equal to theta C, and we can get the phase change caused by human respiration. We select part of signal samples, which can form a circular arc to fill the final circle. Specifically, we detect all peaks and valleys of the respiration waveform in a window, and we treat all neighboring peak to valley and valley to peak waveforms as candidate waveforms. Then we fill the circle using the least square method based on the signal samples in IQ domain according to each candidate waveform. And for each candidate, we get a circle center C, a radius R, and a fitting error E by using this formula, and we choose the circle center with the lowest fitting error as the final circle center. A simple circle fitting method using all the samples also works, but sometimes it fails to obtain the correct circle center where the samples distribute dispersely or have low signal quality. And our method by using part of the samples can solve this problem. Lastly, we can also capture 4 abnormal respiration patterns during overnight sleep, based on the windows identified as other waveforms and respiration detectable waveforms. We combine the waveforms, respiration rate, and respiration depth to detect apnea, tachypnea, Cosmo, and rapid change of respiration rate. And this is part of our system's demo. As shown above, we use the IR-UWB radar to collect 17 nights sleep data from 7 volunteers. And we compare our system with true respiration monitoring method in our overnight dataset. The results shows that our system achieves the lowest respiration rate estimation errors. And we define the respiration detection rate as the ratio of the duration where respiration is detectable over the duration of the entire night's sleep. And we can see that by combining both amplitude and phase, our system not only finds more respiration detectable waveforms, but also reduces the estimation error of respiration rate. And we evaluate the respiration depth detection performance under different situations and positions. Firstly, the subject with chest facing the radar performs normal respiration for 30 seconds, then deep respiration for 30 seconds, and then gradually return to normal respiration. Our method feeds a new circle center every 30 seconds and is able to restore more realistic change in respiration depth under different situations. And no matter under good positions where the phase waveforms are regular, or bad positions where the phase waveforms are disordered to detect respiration. Our method can always get a proper circle center and restore the respiration depth. And our system is also able to capture these four abnormal respiration patterns. In summary, we propose an overnight and fine-grained respiration monitoring prototype. We use the complementarity between amplitude and phase to eliminate the blind spots and enhance the detectable rate. We also propose a circle-fitting-based phase restoration algorithm to restore the signal phase and estimate the real respiration depth. Our prototype provides high detection rates and low estimation errors of respiration rates, and is capable of recognizing for abnormal respiration patterns. So thank you very much for your attention. I hope you enjoy the presentation and feel free to ask any questions.